Although square raster grid cells are by far the most common used in GIS, there's no reason that grid cells necessarily have to be square. And in fact, there are some advantages to other shapes of grid cells. For example, here's a hexagonal grid. And one of the nice things about a hexagonal grid is that if you're measuring the distance from the center of one of these hexagons to any of the hexagons that touch its edge, the distance is always the same, whether it's off to the side or above or below it. This is not the case with square grid cells. With square grid cells, the ones above, below, to the left and right are one distance away, and all of the ones that just touch at a corner are a different distance away. So in some cases, this can make analysis more complicated. This is an example using a regular hexagonal grid, where this is mapping the color of bird eggs throughout the world. And we can see some interesting patterns there, but we can also see that it was easy to do analysis with this because all of the hexagonal grid cells in this example were equally spaced from their neighboring grid cells. So there are other regular grids out there, some triangular grids, some hexagonal, anything that fits well together like that. But there are also irregular grids in GIS. And by far the most famous of these is the Triangulated Irregular Network, or TIN, T-I-N. TINs are often used to display topographic data, to display terrain data, because sometimes terrain changes very quickly, like in the mountains where elevation changes very quickly, and other times, like in like once you get outside of the mountains onto flat areas, the elevation hardly changes at all. So what we can do is we can draw different size triangles where we can use larger triangles where elevation is not changing quickly, and smaller triangles where we're trying to account for more rapid changes in elevation. This shows an example where we can see that out in this flat area here, we're able to use very large triangles. With these triangles, this would be one triangle. The three pink lines would be the edges, and the three yellow dots would be the nodes where we actually have elevation values. So just from those three nodes, we would be able to tell how this is tilted, how this triangle is tilted, and be able to determine the slope and aspect of this data. But we can see out in this flat area, we have very big triangles, and right up near the peaks of these mountains here, we have very small triangles because the elevation is changing much more quickly there. So these TINs are another nice way of representing elevation data. Which brings up the point that there's really no right or wrong way to represent data. And elevation data illustrates that nicely. We could represent elevation data with raster data, such as a digital elevation model, where each grid cell has one elevation value. We could represent it as contours, as shown here, where each one of these contour lines shows a line of equal elevation. Or we could represent it by these TINs, which is basically building a lot of triangles, each oriented to show what the elevation, the slope, and the aspect are in that area there. So elevation is really a nice way of showing that there really is no right or wrong answer, and that different types of geographic data models or spatial data models can be used to represent the same information.